What if you're not the only version of you? Right now, somewhere out there in the vast fabric of reality, another you might be living a life almost identical to yours, or one so wildly different it's unrecognizable. This isn't just science fiction. The idea that our universe is just one of countless others, each with its own twists and turns, is a theory that's fascinated scientists, philosophers, and dreamers for decades. And the deeper we dig, the more shocking the possibilities become. Imagine a world where every decision you've ever made branches off into new realities. One where you took that job offer, another where you never met your best friend, and yet another where the laws of physics themselves are completely alien. These parallel universes aren't just hypothetical playgrounds for storytellers, they're serious scientific concepts, backed by some of the most brilliant minds in physics. From the mind-bending many worlds interpretation to the eerie simulation hypothesis, the theories we're about to explore will challenge everything you thought you knew about reality. But why does this matter? Because the idea of parallel universes forces us to confront the biggest questions of all. Are we alone? Is our existence just a fluke in an infinite cosmic tapestry? And what does it mean for our lives if there are infinite versions of us out there? Strap in, because we're about to dive into 25 of the most shocking theories about parallel universes, theories that will make you question the very nature of reality itself. By the end of this journey, you might never look at the world the same way again. The first and perhaps most mind-bending theory on our list comes straight from the world of quantum physics, the many worlds interpretation. Picture this: every time a quantum particle could go left or right instead of choosing, reality splits. Both possibilities happen, just in separate, branching universes. This isn't some poetic metaphor. In the 1950s, physicist Hugh Everett proposed that our universe isn't a single, linear timeline, but an ever-expanding tree of infinite realities, each sprouting from every possible outcome of every quantum event. Take Schrödinger's famous cat the thought experiment, where a cat in a box is simultaneously alive and dead until someone opens it and collapses the possibility into one outcome. But the many worlds interpretation flips this on its head. There's no collapse. Instead, the moment the box is opened, reality divides. In one universe, you find a purring cat. In another, you're staring at a tragedy. Both are equally real. You just happen to experience one of them. Now scale that up. Every choice, every random atomic twitch, every roll of the cosmic dice doesn't just vanish the road not taken. It becomes its own universe. Somewhere out there, a version of you turned left instead of right this morning. Another version became an astronaut. Another never existed at all. And here's the wild part: none of these universes are more real than the others. They're all humming along in parallel, forever unaware of each other. So why don't we notice this infinite splitting? Imagine standing in a forest where every tree is a universe. You can only see the one you're standing under. The others are hidden, but they're just as solid, just as vivid. That's the eerie beauty of Everett's theory. It suggests that reality isn't just bigger than we imagined, but infinitely, explosively vast. Every moment is a fork in the road, and every path is taken just not by you. At least not this version of you. The many worlds interpretation doesn't just rewrite the rules of physics, it shatters our very understanding of identity and existence. If every possible outcome plays out in some parallel reality, what does that mean for you? Are you the real version, or just one thread in an endless tapestry of selves? Philosophers call this the problem of personal identity, and it's enough to make your head spin. In one universe, you might be reading this on a train to Paris. In another, you skip this video entirely. Neither choice is more you than the other, just different branches of the same cosmic tree. But here's where it gets even stranger. Could these universes ever touch? Most physicists say no. These branches are like ghost ships sailing forever in separate seas, invisible to one another. Yet some theories suggest faint glimmers of interaction. Quantum experiments have detected particles behaving in ways that defy classical physics, almost as if they're responding to forces outside our universe. In 2018, scientists at Yale observed quantum signals that seemed to echo across possible states, like a whisper between realities. It's not proof, but it's a tantalizing hint that the walls between worlds might not be as solid as we think. Think of it like radio static. Most channels are noise, but every so often you catch a snippet of another station bleeding through. If parallel universes exist, could we one day tune into their frequency? The idea isn't pure fantasy. Physicists like David Deutsch propose that advanced technology might eventually let us send signals or even objects across the divide. Imagine a future where you could peek into a universe where dinosaurs never went extinct, or where your favorite fictional stories are real. The ethical questions alone are staggering. Would contacting another version of yourself unravel your sense of self? Could meddling with alternate histories create chaos we can't undo? And then there's the ultimate existential kicker. If every choice spawns a new universe, does free will even exist? Or are we just passengers on an infinite roller coaster of predetermined forks? Some argue the many worlds interpretation actually preserves free will. Your decisions matter because they carve out new realities. Others counter that it's an illusion, with all outcomes playing out simultaneously. Either way, one thing's certain: the universe just got a lot more crowded and a lot more mysterious. If the many worlds interpretation leaves your head spinning, brace yourself, because the bubble universe theory is about to stretch your imagination even further. This idea doesn't just suggest parallel realities. It paints a picture of our entire universe as a single soap bubble floating in an endless cosmic froth, surrounded by countless others, each with its own bizarre set of rules. The story starts with inflation, the explosive expansion of space in the earliest moments after the Big Bang. Most cosmologists agree this happened, but some, like physicist Alan Guth, take it a step further. They propose that inflation never stopped. Instead, it's still happening right now in pockets of reality far beyond our observable universe. Every fraction of a second, new bubble universes pin off from this roiling cosmic foam, each one a self-contained cosmos with its own physics. Some might have stronger gravity, others could have light that moves at a snail's pace, a few might even have extra dimensions woven into their fabric. Here's where it gets wild. These bubbles aren't static, they drift, expand, and sometimes collide. Picture two soap bubbles bumping together in midair. A collision between universes would unleash unimaginable energy, potentially leaving scars on the cosmic microwave background, the afterglow of the Big Bang. In 2010, researchers studying this faint radiation spotted strange, unexplained bruises in the sky, cold spots and irregular patterns that some argue could be echoes of a long-ago crash with another universe. Skeptics wave it off as cosmic static, but if true, it would be the first tangible evidence that we're not alone in the multiverse. Now consider the implications. In one of these bubble universes, stars might form in impossible shapes. In another, time could flow backward. There might even be bubbles where the very concept of matter doesn't exist, just swirling forces we can't begin to comprehend. And here's the kicker: we'll likely never know for sure. The space between these bubbles stretches faster than light can travel, putting them forever out of reach. But that doesn't mean they're not there. So why does this matter? Because if the bubble universe theory is correct, our existence isn't just improbable, it's inevitable. In an infinite multiverse, every possible configuration of reality must exist somewhere. The constants that make life possible in our universe, the exact strength of gravity, the charge of an electron, aren't finely tuned miracles. They're just the lucky numbers we drew in the cosmic lottery. Somewhere out there, another bubble might harbor life that thrives in conditions that would vaporize us instantly. That's the humbling beauty of this theory. It turns the unimaginable into the mundane. The multiverse isn't weird, it's just physics on the grandest scale. What if everything you see, touch, and experience is nothing more than an elaborate illusion, a cosmic projection, like a movie playing on the surface of a distant screen? Welcome to the holographic principle, one of the most radical ideas in modern physics. It suggests our three-dimensional universe, with all its depth and richness, might actually be encoded on a two-dimensional boundary at the edge of space-time, like a hologram etched onto an unseen surface. This isn't just wild speculation. The roots of this theory trace back to black holes, those monstrous gravitational traps where space and time warp beyond recognition. In the 1970s, physicist Jacob Bekenstein discovered something astonishing. The information swallowed by a black hole isn't destroyed. Instead, it's somehow preserved on the black hole's event horizon, the point of no return, like data burned onto a celestial hard drive. Later, Leonard Susskind and Gerard T. Hooft took this further, proposing that all information in the universe could be stored this way, with our 3D reality acting as a projection from a 2D surface we'll never see. Think of it like a credit card hologram. Tilt it one way and you see a flat image, tilt it another, and suddenly it has depth, except in this case, the hologram is everything that exists. Stars, planets, even your own thoughts might just be shadows cast by data flickering on some unimaginably distant boundary. If that's true, then parallel realities could be lurking right there in the code, alternate versions of our world, stacked like layers in a cosmic hard drive waiting to be decoded. But how could we ever test something so bizarre? Enter Fermilab's holometer, a mind-bending experiment designed to hunt for pixelation in space-time itself. Just as a digital image breaks down into grainy squares when you zoom in, the holometer's team theorized that reality might too, revealing its true holographic nature. After years of sensitive measurements, the results were inconclusive, but the door isn't closed. Future experiments using quantum sensors 1,000 times more precise might finally catch the universe in its act of illusion. What would it mean if the holographic principle is real? For starters, it would rewrite the rules of existence. Parallel universes might not be separate realms at all, just different files on the same cosmic server, flickering in and out of view. Time and space could be emergent properties, not fundamental truths, and the very idea of location would crumble. 2 points a billion light-years apart might be adjacent in the underlying code. It's a theory that doesn't just suggest other realities, it implies that all realities are woven from the same strange, flat fabric, spinning the grandest illusion of all. Ever wondered how many different versions of the universe could exist? According to string theory, the most ambitious framework in modern physics, the answer is a number so vast it defies comprehension: 10 to the power of 500. That's a 1 followed by 500 zeros. Each of these mind-boggling possibilities represents a unique vacuum state, a cosmic recipe for reality where the fundamental constants of nature could be completely rearranged. And if even a fraction of these states spawned actual universes, the multiverse would be more diverse than anything we've ever dared to imagine. At the heart of this idea is string theory's radical proposition that the tiniest building blocks of reality aren't particles but vibrating strings of energy. The way these strings oscillate determines everything: the forces of nature, the behavior of matter, even the fabric of space-time itself. But here's the twist: the equations suggest these strings can vibrate in countless ways, each configuration producing a universe with its own unique physics. Some might have 6 dimensions of space, others could have dark energy so weak that galaxies never form. A few might even allow time to loop back on itself like a Möbius strip. Brian Greene, one of string theory's most eloquent champions, compares this to a cosmic landscape, an infinite terrain of possible universes, each perched in its own valley of stability. Our universe is just one hill in this vast terrain, with its particular blend of forces and particles, but step into another valley and the rules could be unrecognizable. Gravity might be 1,000,000 times stronger, turning every planet into a black hole, or electromagnetism could be so feeble that atoms never bond, leaving the universe a soup of lonely particles. The sheer variety is dizzying, and it raises a haunting question. Why does our universe have the settings it does? Critics, though, aren't convinced. Nobel laureate Sheldon Glaser famously dismissed the string landscape as not even wrong, a dazzling mathematical playground with no way to test its predictions. If these alternate universes are forever beyond our reach, how can we ever know they're real? Some physicists argue that without experimental proof, the landscape is just metaphysics in a lab coat, a beautiful story with no grounding in observable reality. Yet supporters counter that absence of evidence isn't evidence of absence. They point to the eerie fine-tuning of our universe, the fact that if gravity or the nuclear forces were even slightly different, life as we know it would be impossible. In a multiverse of 10 to the 500 possibilities, some universe had to hit the jackpot. We just happened to be in the one that did. It's like winning the lottery and realizing someone had to, except the odds are infinitely worse. The debate rages on, but one thing's clear: string theory's landscape forces us to confront the limits of human knowledge. Are we searching for a theory of everything, or are we just ants trying to map a forest we'll never fully see? Whether this is groundbreaking science or untestable speculation, it undeniably reshapes how we think about our place in the cosmos, and that's a conversation worth having, no matter which universe you're in. What if everything you know, every star, every atom, even your own thoughts, is just lines of code in an unfathomably advanced simulation? This is the simulation hypothesis, a theory that's gained traction not just among philosophers, but tech billionaires like Elon Musk, who famously argued the odds we're living in base reality are 1 in billions. At its core, the idea is simple. If civilizations can one day create simulations indistinguishable from reality, and if they choose to run them, the number of simulated minds would dwarf the number of real ones. Statistically, you're probably one of the simulations, but here's where it gets even wilder. If our universe is a simulation, parallel realities might not be alternate dimensions. They could just be other instances of the same program, running simultaneously like tabs in a cosmic browser. Think of it like video game saves. Every time you restart a game, you're not erasing the previous version. You're spawning a new timeline where different choices play out. Now imagine a superintelligence doing this at the scale of entire universes, tweaking variables to see how civilizations rise, fall, or discover they're made of ones and zeros. Philosopher Nick Bostrom laid the groundwork with his trilemma, 3 stark possibilities about our reality. Either 1, intelligent species always go extinct before reaching simulation-level tech. 2, they reach that level but never choose to run ancestor simulations. Or 3, we're almost certainly living in one. The first 2 options are bleak, suggesting humanity is either doomed or disinterested in cosmic experimentation. The third, a mind-bending rabbit hole where reality is just someone else's experiment. So how could we possibly test this? Some scientists suggest looking for glitches in the fabric of reality, tiny errors a lazy programmer might leave behind. Maybe particles behave oddly at certain energy levels, like pixels straining at the edges of a rendered image. Others propose hunting for evidence of computational limits. Just as your laptop struggles with too many open apps, our universe might show signs of lag at extreme scales, subtle delays in quantum interactions, or fuzzy boundaries in black hole physics. Yet, even if we found such clues, would they prove anything? A simulation sophisticated enough to mimic our universe down to quarks and quasars could easily mask its own seams. And if it is a simulation, who's to say the programmers haven't rigged the rules to keep us from ever knowing? This isn't just science, it's a modern twist on age-old questions about the nature of existence. Whether you find the idea terrifying or thrilling, one thing's certain: if the simulation hypothesis is true, then parallel universes might be closer than we think, just another subroutine in the cosmic mainframe. Have you ever rounded a corner and been hit with an overwhelming sense of déjà vu, the eerie feeling you've lived this exact moment before? Or maybe you've spotted a glitch in your peripheral vision, a fleeting shadow, a flicker of light that vanishes when you turn to look. For some, these aren't just odd quirks of the human brain. They're potential cracks in the simulation, tiny errors leaking through from whatever or whoever built our reality. Take the famous double-slit experiment. When scientists fire particles at a barrier with two slits, those particles behave bizarrely. Observed, they act like tiny little bullets passing through one slit or the other. But when no one's looking, they morph into probability waves, passing through both slits simultaneously, as if the universe is optimizing processing power by only rendering details when observed. Sound familiar? It's the same trick video games used to save resources, only loading high-resolution textures when a player looks directly at them. Then there's synchronicity, those uncanny coincidences that feel too perfect to be random. You think of an old friend and they text you moments later. You hum a song and it plays on the next radio station you tune to. Some argue these are hints of background processes tweaking our reality's variables, like an algorithm nudging narratives for dramatic effect. Even quantum entanglement, where particles mirror each other's states instantly across vast distances, fits unnervingly well with a simulated universe. In a game, two objects can communicate faster than light because they're just data points in the same program. But before you start questioning everything, let's pause. Critics roll their eyes at calling these phenomena evidence. Déjà vu has neurological explanations, a hiccup in memory processing, quantum weirdness. Just the rules of an inherently probabilistic universe, and coincidences. Well, with billions of brains generating endless thoughts daily, some overlaps are statistically inevitable. The danger, skeptics warn, is mistaking mystery for proof. After all, if we're meant to find glitches, wouldn't the simulators make them more obvious? Unless, of course, they're toying with us, leaving breadcrumbs just subtle enough to keep us guessing. Yet the debate isn't purely scientific, it's deeply human. Is the simulation hypothesis a revolutionary lens for understanding reality, or just existential escapism dressed in tech jargon? For some, it's comforting. If life is a simulation, maybe suffering has meaning, a narrative arc coded by higher designers. For others, it's terrifying. What if the simulators hit delete one day, and then there's the ultimate irony? If we are simulations, wouldn't our creators likely be simulations too, trapped in an infinite regression of fake realities? Here's the twist: the simulation hypothesis might never be provable. Even if we found irrefutable glitches, how could we distinguish an actual simulation from a universe with inherently odd rules? Maybe the answer isn't in hunting errors, but in asking why we're so drawn to the idea. After all, every culture has myths of fabricated realities, from Plato's cave to Hindu Maya. Perhaps the real glitch is our timeless need to believe there's something, anything beyond the curtain. And that's a code no science can crack. Imagine this: you're playing Russian roulette with a gun that has 1,000,000 chambers and only one bullet. Statistically, you should survive, but quantum mechanics suggests something far stranger. According to the theory of quantum immortality, you always survive not by luck, but because your consciousness must continue in a universe where you don't die. Your experience of reality, in other words, can never include your own death. It's not just a wild thought experiment. This idea emerges directly from the many worlds interpretation, where every possible outcome of every event branches into a new universe. Here's how it works. In the quantum suicide thought experiment, a hypothetical device is set up to kill or spare you based on a random quantum event like the decay of a single atom. If the atom decays, the gun fires. If not, it doesn't. Traditional logic says you have a 50-50 chance each time. But proponents of quantum immortality argue that from your perspective, you'll always find yourself in the universe where the gun doesn't fire. Why? Because in the branches where you die, your consciousness ceases, meaning you can't experience those outcomes. The only realities you'll ever know are the ones where you're still alive, no matter how improbable. This leads to some unsettling conclusions. If quantum immortality is real, aging, disease, even fatal accidents might not be the end. Your consciousness could keep hopping to realities where you persist, like a ghost slipping between cracks in existence. Picture a car crash where 99 out of 100 versions of you perish, but you only remember the one where you walked away unscathed. It's a cosmic version of survivorship bias, where the only observer left is the one who, by definition, can't witness their own demise. Ethicists recoil at the implications. If consciousness is eternally self-preserving, does that mean we're trapped in an endless loop of near misses? Could suffering be prolonged indefinitely in some branching timeline? And what about identity? If you split with every decision, which version is really you? Philosopher David Chalmers once quipped that this scenario turns death into an illusion of the first-person perspective, a trick played by probability on the human mind. But critics push back hard. They argue that quantum immortality conflates subjective experience with objective reality. Just because you don't experience death doesn't mean it doesn't happen. In most branches, you still die. Your surviving self is just a statistical outlier. Worse, the theory might encourage reckless behavior if taken literally. No, you shouldn't test it by jumping off a building. Statistics guarantee most of your branching selves won't land softly. Yet the idea lingers because it taps into something primal, our terror of oblivion. If consciousness is truly tied to quantum outcomes, then death might not be a wall but a hall of mirrors, reflecting endless versions of ourselves, each stepping into the next frame just before the lights go out. Whether that's science or science fiction, it forces us to ask, what does it mean to survive if survival itself is just another twist in the multiverse's kaleidoscope? What if there's a universe where time runs backward, atoms are built from antimatter, and your reflection isn't just a trick of light, it's another version of you? This isn't the plot of a sci-fi movie. It's a serious prediction born from one of physics' most fundamental symmetries, CPT, short for charge parity and time reversal. CPT symmetry suggests that for every particle in our universe, there's a mirror image counterpart with opposite charge, spin, and direction in time. And if that symmetry holds perfectly, it implies the existence of an entire mirror universe, one where causality flips like a rewinding tape. Let's break this down. In our world, electrons are negatively charged. In the mirror universe, they'd be positively charged positrons. Our matter would be their antimatter. Even time itself would flow in reverse, meaning their Big Bang might be our distant future. At first glance, this sounds absurd, but the math checks out. When physicists apply CPT transformations to the equations governing reality, the results still hold. Nature, it seems, doesn't care which way time runs, at least not on paper. So where's the evidence? CERN Alpha experiment has been trapping anti-hydrogen atoms, antiprotons paired with positrons, to see if they behave identically to normal hydrogen. So far, they do mostly, but tiny deviations could crack open the door to this mirror realm. Imagine if antimatter fell up instead of down in gravity, or if positrons aged slightly faster than electrons. These anomalies would hint that the mirror universe isn't just hypothetical, it's leaking into ours. Here's where cosmology gets messy. If the mirror universe exists, why don't we see equal amounts of matter and antimatter? After the Big Bang, both should have annihilated each other, leaving nothing but energy. Yet here we are in a matter-dominated cosmos. Some theorists propose the mirror universe did form, but repelled ours during inflation, creating a parallel space-time bubble where antimatter rules. Others suggest we're seeing shadows of it in cosmic anomalies like galaxies that spin the wrong way or particles that seem to remember the future. The wildest implication: if time flows backward there, does that mean our future is their past? Could a mirror version of you right now be living your life in reverse, unaware that your choices ripple backward into their reality? It's a dizzying thought, one that challenges not just physics but the very meaning of cause and effect. Whether this mirror world is real or just a mathematical quirk, one thing's certain: the universe just got a lot stranger. And we're only beginning to glimpse its reflection. What if the end of our universe isn't an ending at all, but the start of something new? Roger Penrose, the Nobel Prize-winning physicist who helped uncover the secrets of black holes, proposed a radical vision of reality where time is an endless loop, and universes cycle through death and rebirth like cosmic seasons. This is conformal cyclic cosmology, a theory so audacious it rewrites the entire life story of existence. At the heart of Penrose's idea is a paradox. As the universe expands, galaxies drift apart, stars burn out, and black holes evaporate. Eventually, all matter decays into faint particles drifting through an icy void. Traditional cosmology calls this the heat death, a lifeless, eternal twilight. But Penrose asks, what if that cold, empty state becomes the Big Bang of a new universe? His math shows that when all particles lose their mass and the cosmos stretches into infinite thinness, the distinction between end and beginning blurs. Time itself resets and a new universe erupts from the ashes of the old. The key lies in black holes, those cosmic shredders that trap light, warp space, and hide singularities where physics breaks down. Penrose argues they're not just destroyers, they're time capsules. As black holes evaporate over eons, they release unimaginable amounts of entropy, a measure of disorder. But instead of vanishing, that entropy might imprint itself onto the fabric of spacetime, leaving faint geometric signatures called Hawking points. These would be like cosmic tattoos, remnants of a previous universe's black holes embedded in the newborn cosmos. Now here's where it gets controversial. In 2010, Penrose and his team claimed to find evidence of these imprints in the cosmic microwave background, the afterglow of the Big Bang. They pointed to swirling patterns called B-mode polarization, arguing these were gravitational waves from collisions of supermassive black holes in a prior universe. Mainstream cosmologists weren't convinced. Many dismissed the patterns as cosmic dust or statistical noise. But if Penrose is right, those faint ripples could be echoes of universes long gone, whispering across eternity. Imagine standing on a frozen lake, listening for the cracks of ice forged seasons ago. That's what physicists are doing, tuning into the faintest signals to decode history beyond history. If cyclic cosmology is real, our universe is just one page in an infinite cosmic novel, each chapter written in the entropy of black holes and the geometry of spacetime. And somewhere out there, another version of you might be reading these same words, not in a parallel reality, but in the next cycle of existence when time begins again. What if black holes aren't just cosmic vacuum cleaners but cosmic wombs? This is the daring idea behind the black hole multiverse theory, where every singularity might be the seed of an entirely new universe, hidden behind the event horizon like a cosmic matryoshka doll. At first glance, it sounds like science fiction, but physicist Lee Smolin gave it a startling twist with his theory of cosmic natural selection, a radical proposal that universes evolve, and black holes are how they reproduce. Picture a black hole's core, the singularity, where gravity crushes matter into an infinitely dense point. Traditional physics says this is where equations break down and predictability ends. But what if that's not the end? Some theories suggest the extreme conditions inside a singularity could trigger a new Big Bang, birthing a universe with slightly tweaked physics. In this scenario, our own universe might have formed inside a black hole from a parent cosmos, and every black hole in our reality could be spawning its own baby universe right now, invisible to us. Smolin took this further, arguing this process could explain why our universe seems so finely tuned for life. If each new universe inherits slightly altered physical constants from its parent, like cosmic DNA mutations, then over countless generations, universes that produce more black holes would dominate. Think of it like natural selection, but on a cosmic scale. Universes that optimize black hole production survive by creating more offspring, while those that don't fade into obscurity. If true, it means our universe isn't designed for life. It's designed for black holes, and life is just a side effect. But how could we ever test such a mind-bending idea? One clue might lie in the cosmic microwave background. If our universe was born from a singularity, it could carry imprints of its parent's geometry, subtle asymmetries or anomalies in the afterglow of creation. Some researchers even speculate that dark energy, the mysterious force accelerating our universe's expansion, could be a relic of the birthing process, like a gravitational echo from the other side of the singularity. Critics, though, aren't sold. They argue there's no mechanism to transmit physical constants from parent to child universes, making Smolin's theory more poetic metaphor than hard science. Others counter that without observable proof, the idea is untestable, a philosophical thought experiment dressed in equations. But supporters fire back. If black holes truly are universes in disguise, wouldn't the very nature of their event horizons make direct observation impossible by definition? Here's the kicker. If this theory is correct, you might be living inside a black hole right now. Our entire cosmos could be nestled within the singularity of some grander universe, with its own stars, black holes, and civilizations unknowingly hosting their own cosmic offspring. It's a dizzying, fractal vision of reality, one where creation isn't a one-time event, but an endless cycle of collapse and rebirth, hidden behind the darkest curtains of space-time. And that raises the ultimate question. If black holes are cosmic nurseries, does that make us the ancestor or the descendant in this infinite chain of existence? Picture our universe not as an infinite expanse, but as a single slice of bread floating in a vast, hidden dimension, one slice among countless others in an unimaginably grand cosmic loaf. This is the bizarre yet compelling vision of the membrane multiverse, or brain world scenario, emerging from the depths of M-theory, the elusive framework that unites string theory's tangled equations. Here, parallel universes aren't just distant copies, they're physical membranes or brains, stacked like pages in a book, hovering mere millimeters apart in higher dimensional space. Yet those millimeters might as well be light years, because in this model, everything we experience, light, matter, even time, is glued to our brain, forever cut off from the others. But there's one cosmic rule breaker: gravity. Unlike other forces which are bound to our brain like paint on a canvas, gravity might be the only thing that leaks into the bulk, the higher dimensional space between brains. This could explain why gravity is so weak compared to other forces. A magnet can lift a paperclip against Earth's entire gravitational pull, as if gravity's strength is diluted by spilling into other dimensions. In the late 1990s, physicists Lisa Randall and Raman Sundram showed how this leakage might warp spacetime itself, creating gravity wells that pull objects toward our brain like how a bowling ball dimples a bedsheet. Now for the smoking gun. If gravity slips between brains, it could leave fingerprints in our universe. Some astrophysicists hunt for graviton echoes, hypothetical particles that carry gravity, and might briefly vanish into the bulk before snapping back, like a ball ricocheting between walls. Others study the cosmic microwave background for anomalies, like temperature fluctuations that suggest gravity behaved differently in the early universe. Then there's the wildest possibility of all: brain collisions. If another universe brain drifted too close to ours in the higher dimensional bulk, the collision could unleash energy exceeding 1 trillion nuclear bombs, potentially leaving scars in our sky. Some speculate the Big Bang itself was one such collision, a cosmic car crash birthing our reality. What's unnerving is how close these parallel worlds could be. In some models, another brain might hover just a millimeter away in a fourth spatial dimension, forever invisible because light can't cross the gap. Imagine living in a house of mirrors where every reflection is a fully realized universe, pressing against the glass, yet you'll never touch, never see, never know. Skeptics argue this is all mathematical fantasy. Without direct proof of extra dimensions, brain worlds remain elegant speculation. But supporters counter that the same math predicting brains also solves stubborn problems, like why the universe's expansion is accelerating. Whether M-theory's vision holds or not, it offers something profound. A universe where the walls between realities aren't light years apart, but closer than your own skin. And that changes everything. Gravitational waves, the ripples in spacetime first detected in 2015, might hold the key to proving we're not alone in the cosmic loaf. If parallel brain universes exist, their collisions could send shockwaves through the higher dimensional bulk, leaving faint tremors in our own spacetime. These wouldn't be the familiar waves from black hole mergers, but something far stranger, discordant frequencies, patterns that don't match any known astrophysical event, like hearing a thunderclap with no storm. The Laser Interferometer Gravitational Wave Observatory, or LIGO, is already hunting for these anomalies. Just as a seismograph detects earthquakes, LIGO ultra-sensitive lasers measure distortions in spacetime smaller than a proton. Most signals fit neatly into categories: colliding neutron stars, spiraling black holes. But what if they caught a wave that defies explanation? One candidate, a hyper-energetic burst with no optical counterpart, lasting mere milliseconds but packing the punch of a supernova. Some theorists argue this could be the echo of a brain collision from billions of years ago, a cosmic car crash reverberating through the bulk. Critics, though, call this a Hail Mary for string theory, a last-ditch hope for evidence where none exists. After all, unexplained signals could just be noise or undiscovered astrophysics within our own universe. Even if LIGO detected something bizarre, proving it came from another brain would require ruling out every mundane possibility first. And that's assuming brain collisions leave detectable waves at all. The math suggests they might resemble cosmic strings, hypothetical defects in spacetime, but these too remain unproven. Yet the stakes couldn't be higher. If gravitational waves ever revealed a brain collision, it would rewrite physics overnight. Suddenly, extra dimensions wouldn't be abstract math but observable reality. String theory's critics would face hard evidence instead of philosophical gripes, and humanity would grapple with a truth more unsettling than aliens: that we're forever separated from infinite neighbors by a gap we can't cross, like ants on a windowpane, unaware of the world beyond the glass. The search continues. Upgraded detectors like the Einstein telescope with 10 times LIGO sensitivity could sift the cosmic static for these ghostly fingerprints. Until then, the brain world multiverse remains a tantalizing what-if, a theory clinging to the hope that somewhere in the static of spacetime, another universe once brushed against ours and left a scar. Numbers aren't just tools for counting or calculating. What if they're the very fabric of reality? This is the bold claim at the heart of Max Tegmark's mathematical universe hypothesis, a theory so audacious it suggests every possible mathematical structure isn't just an abstract idea but a physical universe. In other words, if an equation can describe a cosmos, that cosmos exists somewhere in the multiverse. No matter how bizarre, no matter how alien, if the math checks out, the universe is real. Tegmark's vision strips reality down to its purest form. Forget particles, forces, or even space and time. At the deepest level, everything is mathematics. Our universe isn't described by numbers, it is numbers. Think of it like a video game. The worlds we explore on screen aren't made of atoms, they're made of code. In Tegmark's view, our reality is the same, a cosmic simulation where the programming language is math itself. And just as a game engine can generate endless virtual landscapes, the source code of existence generates endless universes, each governed by its own mathematical rules. Now, here's where it gets even wilder. Some of these mathematical universes might be unrecognizable to us. One could have 17 dimensions, another might lack the concept of time entirely, and yet another could run on geometry so twisted that circles have corners. But there's also a hauntingly beautiful possibility. The constants we take for granted, like pi, the ratio of a circle's circumference to its diameter, might not be fixed. In some universes, pi could equal 4 or 1,000,000 or an imaginary number. The circles in those worlds wouldn't just look different, they'd defy everything we know about logic itself. But is this science or just philosophy in a lab coat? Critics argue Tegmark's hypothesis is untestable, a dazzling thought experiment with no way to verify it. After all, if other mathematical universes are forever beyond our reach, how can we ever prove they're real? Even Tegmark admits his idea sits on the edge of metaphysics. Yet supporters counter that it solves a profound puzzle: why math is so eerily effective at describing reality. From Newton's laws to quantum mechanics, the universe obeys mathematical rules with uncanny precision. If math isn't just a human invention but the underlying language of existence, that precision suddenly makes sense. Then there's the pi paradox. If alternate versions of pi define alternate realities, could cracking pi's deeper mysteries unlock doors to other universes? Mathematicians have calculated pi to trillions of digits, searching for hidden patterns. Some speculate that if pi ever stopped being irrational, if its digits suddenly repeated, it would imply our universe is a simulation with finite computational power. Others imagine alien civilizations communicating through pi's infinite sequence, embedding messages in its digits like cosmic Morse code. Yet the real shock of Tegmark's theory isn't just the existence of other worlds, it's the idea that nothing else exists. No gods, no simulators, no underlying quantum fields, just math, cold and pure, generating realities like a calculator spitting out solutions. It's a vision both exhilarating and terrifying. A multiverse where everything that can exist does exist, and we're just one equation in an endless textbook of cosmic possibilities. Whether you find it inspiring or unsettling, one thing's clear: if Tegmark is right, reality is far stranger than we ever dared to dream. Time doesn't flow in a straight line, it fractures. Every second, every choice, every twist of fate could be splintering reality into countless alternate timelines, not through quantum mechanics, but through the sheer force of possibility. This is the time-split multiverse, a theory where parallel realities aren't born from particles but from the ticking clock itself. And the implications are spine-tingling. Somewhere out there, versions of you are living every path time could have taken, from the mundane to the unimaginable. Take the timequake paradox, a thought experiment that pits cause against effect in a loop of pure chaos. Imagine a futuristic lab where scientists build a device capable of sending a single moment backward in time, just a fraction of a second. They test it, and the machine works too well. That tiny ripple cascades, rewriting history in unpredictable ways. A scientist's coffee cup shatters a second earlier, startling her into dropping a crucial component. The lab explodes, and the blast sends another ripple backward, creating a feedback loop of shifting timelines. In one version, the lab never existed. In another, the experiment succeeded beyond their wildest dreams. But here's the catch: all these timelines are equally real, branching from that single manipulated moment like cracks in glass. Then there's Tipler's cylinder, a hypothetical cosmic megastructure so massive, so dense, it doesn't just bend space, it twists time into a knot. Physicist Frank Tipler proposed that if you could spin a cylinder of ultra-dense matter fast enough, it would drag space-time around it like a whirlpool, creating closed time-like curves. Translation: time loops. If you orbited this cylinder in just the right way, you'd find yourself returning to your own past, watching history replay with subtle or catastrophic differences. Some versions of you might never approach the cylinder, others might touch it and vanish into a paradox, and in at least one timeline, you'd become your own ancestor, blurring the line between past and future until the very idea of now collapses. What makes the time-split multiverse so chilling is how personal it gets. Forget Schrödinger's cat, this is your life splintering with every heartbeat. That text you almost sent but deleted, there's a timeline where you hit send and it changed everything. The job you turned down, another you took it and now lives in a penthouse or a prison. Even the universe isn't immune. Cosmic time splits could explain bizarre anomalies like galaxies that appear older than the Big Bang or stars that seem to remember futures that never were. Skeptics argue that without quantum weirdness, time splits are just poetic license, a fancy way to say what if. But supporters point to Einstein's own equations, which allow for time loops under extreme conditions. And then there's the haunting question: if time can branch, how do we know we're in the original timeline? Maybe we're the offshoot, living in the shadow of a reality that took a different turn long before humans existed. The chilling beauty of this theory is that it doesn't require strange particles or hidden dimensions, just the relentless, branching flow of time itself. And if it's true, then right now, in some unseen corner of existence, another version of you is reading these words seconds before or centuries after you are. The only difference is the clock. What if the universe isn't just aware of us? What if it's aware because of us? This is the radical premise of the conscious universe theory, where consciousness isn't a byproduct of reality, but the very force that shapes it. At the heart of this idea lies the von Neumann-Wigner interpretation, a fringe but fascinating take on quantum mechanics, suggesting that it's not detectors or instruments that collapse quantum probabilities into definite outcomes, it's minds. In other words, without an observer, reality remains a blur of possibilities. Without consciousness, the universe might not even be fully real. The classic double-slit experiment hints at this eerie connection. When particles are fired at a barrier with two slits, they behave like waves unless someone observes them. Then they snap into definite particles. But here's the twist: it doesn't matter if the observer is a human, a camera, or a rat. What matters is the measurement, the moment information becomes concrete. Von Neumann and Wigner took this further, arguing that only a conscious observer truly finishes the job, turning quantum fog into solid reality. It's as if the universe is waiting for someone to look before it decides what to be. This idea dovetails with panpsychism, the ancient philosophy claiming consciousness isn't unique to brains but is a fundamental feature of the cosmos, like space, time, or gravity. Rocks, stars, even electrons might have some rudimentary form of experience, not as rich as human thought but as a basic capacity to feel their existence. Modern panpsychists like philosopher David Chalmers suggest that if consciousness is woven into the fabric of reality, it could explain why our observations seem to mold quantum behavior. The universe isn't just reacting to us, it's responding like a dance partner attuned to our every move. Critics, of course, scoff at this as metaphysical hand-waving. If consciousness collapses reality, they ask, what about prehistoric eras before observers existed? Did the universe exist in a hazy half-state until life evolved? Some theorists counter that consciousness could be retroactive, the present observing the past, like a cosmic version of the "if a tree falls" paradox. Others propose that even inanimate objects observe each other through interactions, creating a web of mutual collapse, but the hardest pill to swallow. If consciousness is fundamental, then we might be the universe's way of understanding itself, fleeting fragments of a grand mind waking up to its own existence. The implications are staggering. If the conscious universe theory holds, reality isn't a fixed stage but an interactive tapestry woven by observation. Every thought, every glance, every measurement might not just perceive the world, it could create it. And that leaves us with a haunting question. If consciousness builds reality, what happens when we stop looking? Does the moon still exist when no one's there to see it? Or does it flicker back into quantum potential, waiting for the next observer to call it into being? The answer might rewrite not just physics, but the very nature of existence itself. In 2008, NASA, a scientist studying the cosmic microwave background, stumbled upon something that shouldn't exist, a strange, ominous current in the fabric of space itself. Hundreds of galaxy clusters, each weighing as much as 1,000,000 billion suns, were all streaming in the same direction at inexplicable speeds, like leaves caught in a hidden cosmic river. This wasn't just random motion. It was a coordinated rush towards something outside our observable universe. They called it dark flow, and it might be the first tangible proof we're not alone in the multiverse. The discovery sent shockwaves through cosmology. According to Einstein's theory, matter in the universe should scatter evenly after the Big Bang, like ink droplets in water. But these galaxies were defying the rules, pulled toward a single patch of sky near the constellations Centaurus and Vela. The force required to move them would dwarf anything known to physics, something beyond the reach of our universe's gravity. Theorists proposed a jaw-dropping explanation: a massive, unseen structure lurking in the unobservable cosmos, so enormous its gravitational pull reaches across the void between universes. Picture a mountain so tall its shadow falls into another valley. Now imagine that mountain is another universe and the shadow is bending ours. Critics weren't convinced. They argued instrument glitches, statistical flukes, or even the ghostly imprint of our own galaxy's motion could explain the data, but the dark flow refused to vanish. Later studies, including one in 2010 using the Planck satellite, found the same eerie motion. The numbers were undeniable: over 800 galaxy clusters, some nearly 3 billion light-years apart, all racing toward the same unseen attractor at speeds exceeding 2 million miles per hour. If this wasn't a measurement error, it hinted at something far bigger, a neighboring universe with gravity so strong it warps ours like a magnet tugging at iron filings. The implications are staggering. If dark flow is real, it suggests universes aren't just floating alone in the void, but can interact through forces we don't yet understand. Some models even propose these cosmic titans could collide, sending shockwaves through spacetime. Others speculate the flow points to a parent universe, a higher dimensional realm that birthed ours in a black hole, its gravity still gently pulling at the fabric of our existence. Yet the mystery deepens. Why does the flow align so precisely with our solar system's motion? Is it a coincidence, or does it hint that even our place in the cosmos isn't random? And if other universes can tug on ours, what happens when we tug back? The data remains controversial, but one thing's certain: dark flow is either the most embarrassing error in modern cosmology, or the first thread in a tapestry of realities we're only beginning to unravel. Imagine floating alone in an endless, empty void, no stars, no planets, just infinite blackness stretching for eternity. Now picture this. Suddenly, out of pure random chance, atoms collide in just the right way to form a fully functioning human brain, complete with memories, thoughts, and the eerie conviction that it's always existed in a real world. This isn't the plot of a horror story. It's the Boltzmann brain paradox, one of the most unsettling thought experiments in modern cosmology, and it threatens to unravel everything we think we know about reality. The idea traces back to Ludwig Boltzmann, the 19th century physicist who helped decode the mysteries of entropy. He proposed that in an infinite universe, even the most improbable events must happen eventually given enough time. Monkeys randomly typing Shakespeare isn't just possible, it's inevitable. Fast forward to today, and some theorists argue this logic applies to consciousness itself. In an eternal multiverse where quantum fluctuations can spawn particles out of nothing, couldn't those same fluctuations accidentally assemble a self-aware mind, complete with fabricated memories of a life it never lived? Here's where it gets existential. If Boltzmann brains are possible, how do you know you're not one? Your memories, your sense of identity, even your belief in an external world, what if all of it is just a fleeting illusion, a cosmic accident destined to dissolve back into chaos moments after it forms? The statistical odds are vanishingly small, but in an infinitely old multiverse, impossible loses meaning. Given enough time, Boltzmann brains would outnumber real minds like grains of sand next to a single drop of water. So why aren't we all Boltzmann brains? Physicists split into two camps. Some, like Sean Carroll, argue the paradox exposes a fatal flaw in certain cosmological models, especially those predicting an eternal, chaotic multiverse. If a theory implies you're more likely to be a random fluctuation than a real person, maybe the theory is wrong. Others dismiss it as philosophical sleight of hand. Sure, Boltzmann brains could exist, they say, but if they flicker in and out of existence too quickly to observe anything, they're irrelevant to our universe's measurable structure. Yet the paradox lingers like a ghost in the equations. It forces us to confront the fragility of our assumptions. After all, science relies on the belief that our observations reflect an objective reality. But if randomness can counterfeit entire minds, how do we trust any of our perceptions? The night sky, the laws of physics, even the passage of time, could they all be the elaborate hallucinations of a brain that popped into existence 5 seconds ago? Perhaps the most chilling resolution comes from quantum Darwinism, the idea that only stable, repeatable structures leave lasting imprints on reality. Boltzmann brains, by definition, are unstable. They're cosmic mayflies, here and gone in an instant. Meanwhile, we exist in a universe where matter clumps into galaxies, stars, and planets, creating observers who consistently verify each other's reality. In this view, the very fact that we're debating Boltzmann brains suggests we're not them. But the question remains, in the infinite froth of the multiverse, how many lonely minds flicker into darkness before one of them gets it right? What if the Big Bang wasn't the beginning, just the latest collision in an endless cosmic war between higher dimensional worlds? Enter the ekpyrotic universe, a radical theory where our universe wasn't born from a fiery singularity, but from the wreckage of two towering brains, ghostly membranes of reality, slamming together in a hidden dimension. Forget expansion from a single point. Picture instead a slow-motion car crash between cosmic titans, their impact so violent it forged everything we know, stars, galaxies, even time itself. The idea builds on string theory's brain worlds, where our universe is a three-dimensional sheet floating in a higher dimensional bulk. But in the ekpyrotic model, there's another brain lurking nearby, parallel to ours like a phantom twin. Normally, these brains drift apart, cold and empty, but gravity inevitably pulls them back, culminating in a cataclysmic collision. That collision doesn't destroy, it resets. The energy of impact becomes matter, the shockwaves become quantum fluctuations, and a new universe erupts from the chaos. And here's the kicker. This cycle could have happened infinite times before, with universes rising and falling like waves in an eternal ocean. Critically, this isn't just a prettier version of the Big Bang. Inflationary cosmology says the early universe expanded exponentially faster than light, smoothing out wrinkles in space-time and leaving behind the cosmic microwave background's faint glow. But the ekpyrotic model claims those same patterns could come from brain collisions. The wrinkles aren't quantum noise, but cosmic bruises from the crash. Proponents point to subtle anisotropies in the CMB, unexpected cold spots and swirls that they argue align better with a cyclic universe's geometry than inflation's predictions. Yet the debate rages. Inflation supporters fire back that their theory explains observed CMB patterns too well to discard. The Planck satellite's precise measurements of the microwave background's temperature variations fit inflationary models like a glove, while ekpyrotic scenarios require fine-tuning to match. Worse, critics argue there's no mechanism to reliably separate colliding brains after impact without one. They just stick together like glue, ending the cycle forever. But the ekpyrotic vision holds a haunting allure. If true, our universe is trapped in an endless loop of destruction and rebirth, each cycle subtly different from the last. Galaxies form, civilizations rise, and black holes evaporate, only for everything to be wiped clean and reborn in another collision. Time itself becomes a flat circle with no true beginning or end, just an infinite parade of cosmic seasons. And somewhere in the higher dimensional dark, another brain is drifting toward us right now, carrying the seeds of our universe's next incarnation. The only question is, when it hits, will anyone be left to remember? The act of looking at something doesn't just reveal reality, it might create it. At the heart of quantum mechanics lies a puzzle so baffling it's been debated for nearly a century: the measurement problem. Take the infamous double-slit experiment, where particles behave like waves when unobserved, spreading out in fuzzy probabilities, but snap into definite positions the moment someone measures them. It's as if the universe is a shy performer, changing its act the second it senses an audience. But what happens when the audience itself becomes part of the experiment? Enter Wigner's friend, a thought experiment that turns this quantum quirk into a full-blown paradox, exposing how observers might spin reality into entirely separate parallel narratives. Here's how it works. Imagine Eugene Wigner, a physicist, stands outside a lab while his friend conducts the double-slit experiment inside. Before Wigner looks, the particle exists in a superposition, all possible paths at once. His friend, however, sees a definite result the moment they measure it. Now comes the twist. From Wigner's perspective outside the lab, his friend is still part of the quantum system, meaning their observation hasn't collapsed anything yet. To Wigner, his friend is now in a superposition too, simultaneously having seen every possible outcome until he opens the door and asks what happened. Two observers, two irreconcilable realities, and no way to say which one is true. This isn't just abstract musing. Modern labs have scaled up Wigner's scenario using photons and beam splitters, showing that observers really can record conflicting versions of the same event. In 2019, researchers in Vienna demonstrated this with a quantum twist on the classic paradox, proving that facts, even about simple measurements, can be subjective. One detector saw a photon take one path, another, entangled with the first, insisted it took another. Both were right, but only within their own observational bubble. The unsettling implication: reality might not be a fixed script, but an improvised play where each observer gets their own private performance. Now, stretch this idea to its limits. If consciousness plays a role in shaping reality, could there be universes where every possible observation does happen, just to different observers? Some interpretations suggest yes. In these scenarios, Wigner's friend doesn't just see one outcome, they split into multiple versions, each experiencing a different result. The universe fractures not just at quantum events, but at the very moment of perception, spawning countless threads where every glance, every measurement spins off new worlds. One version of you reads these words in a universe where quantum rules are obvious, another in a reality where particles behave classically. Neither is more real, just witnessed by different yous. Critics, of course, recoil at giving consciousness such cosmic weight. They argue decoherence, quantum noise from the environment, explains collapse without invoking observers. A photon doesn't need a mind to choose a state. Air molecules or stray photons jostling it can do the job. Yet even this doesn't resolve Wigner's core dilemma: who or what counts as an observer? A human, a camera, a single atom, the boundary remains blurry, and with it, the line between reality and perception. The stakes couldn't be higher. If observation creates reality, then the universe isn't a cold, indifferent machine. It's a collaborative artwork partially painted by our attention. Ancient mystics spoke of a participatory cosmos. Quantum physics might be proving them right. And lurking beneath it all is the gnawing question. If reality bends to the observer, what happens when nobody's looking? Does the moon really exist when we turn away? Or does it dissolve back into quantum potential, waiting for the next glance to call it into being? The answer might rewrite not just physics, but the story of existence itself. Black holes famously devour everything, even light, but what if their opposites exist, not as cosmic vacuum cleaners, but as cosmic fire hoses, spewing out matter and energy into entirely new realities? Enter the white hole multiverse, a mind-bending hypothesis suggesting that every black hole in our universe might be secretly birthing a new universe through its theoretical twin, a white hole. Unlike their dark counterparts, white holes can't be entered, only exited. They're like one-way doors out of space-time, ejecting everything they contain into a fresh cosmos with its own laws of physics. And if this theory holds, it would mean our universe could have been born in the white hole of a parent universe's dying black hole, a cosmic Russian nesting doll stretching back to infinity. This idea isn't pure fantasy. It emerges from the cold equations of general relativity, which mathematically allow for white holes just as they predict black holes. The catch: no one's ever observed one yet. Some speculate that white holes could explain bizarre cosmic explosions, like gamma-ray bursts with energy signatures that defy conventional astrophysics. Others theorize that the Big Bang itself might have been a white hole event, a singularity not collapsing but erupting, spraying space-time into existence like a geyser of reality. Stephen Hawking's work on black hole radiation adds another layer. If black holes slowly evaporate over eons, leaking energy via Hawking radiation, could their deaths trigger white hole formation? Picture a black hole shrinking to nothing, its final moments of collapse rebounding like a compressed spring, launching a new universe into being. This connects to the Big Bounce hypothesis, where the death of one universe becomes the birth of another in an endless cycle of contraction and explosion, no singularity required. Instead of a fiery Big Bang, our universe might have been a gentle bounce, a white hole's quiet exhale after a black hole's final gasp. The implications are staggering. If every black hole spawns a new universe, then our cosmos could be teeming with unborn realities, each nested inside the event horizons of the black holes we've observed. The supermassive beast at the center of our Milky Way, it might be incubating an entire cosmos right now, utterly invisible to us. Even stranger, the laws of physics in those newborn universes could be subtly or drastically different from ours. Entropy might flow backward, gravity could repel instead of attract, time itself might unfold in loops rather than a straight line. Critics dismiss white holes as mathematical curiosities with no basis in observable reality. After all, if they eject matter, why haven't we detected a single one? Some physicists argue that white holes are inherently unstable, collapsing the instant they form under the weight of their own absurdity. Others counter that they do exist, but only in the distant past or future, or in regions of space-time forever cut off from our view. Yet the theory lingers because it solves two cosmic puzzles at once. First, it offers a plausible mechanism for universe creation without invoking a singular beginning. Second, it suggests an answer to the haunting question of what happens inside a black hole's singularity. Instead of a dead end where physics breaks down, it's a bridge, a tunnel to somewhere new. And if that's true, then every black hole isn't a grave, it's a cradle. A secret passage, a cosmic womb humming with the possibility of infinite new worlds. What if universes evolve just like life on Earth, with natural selection favoring the ones most fit to survive. This is the radical premise of quantum Darwinism, a theory suggesting that the laws of physics aren't arbitrary rules but the result of a cosmic survival game where only the most stable universes thrive. At the heart of this idea is Lee Smollen's fecund universes hypothesis, a twist on the black hole multiverse that turns cosmology into something eerily akin to biology. Imagine universes competing for longevity, spawning offspring with slight mutations, and passing down traits that determine whether they flourish or fade into oblivion. Smollen's vision hinges on black holes as cosmic reproduction engines. Every time a black hole forms in a universe, he proposes, it births a new universe inside its singularity, but with a catch. The fundamental constants of physics in that newborn universe aren't perfect copies. They're tweaked like genetic mutations in DNA. Some variations might render the offspring universe sterile, incapable of forming stars, atoms, or even new black holes. Others might optimize black hole production, leading to a prolific lineage of universes that dominate the multiverse landscape. Over countless generations, universes that produce more black holes would outnumber those that don't, explaining why we find ourselves in a cosmos seemingly fine-tuned for their creation. Here's the kicker: this theory makes testable predictions. If Smollen is right, the laws of our universe shouldn't just allow black holes, they should maximize them. That means certain constants, like the mass of protons or the strength of nuclear forces, should sit at values that make black holes as common as possible without destabilizing reality. Surprisingly, our universe's numbers fit this eerie sweet spot. Even the cosmological constant, the mysterious force accelerating cosmic expansion, is just weak enough to let galaxies and thus black holes form, but not so weak that gravity crumples everything too soon. Critics pounce on this as circular reasoning. If we're here to observe these constants, of course they seem perfectly tuned for our existence, a classic example of survivorship bias. But Smollen counters with a daring rebuttal. If his theory is correct, we should never observe universes where black holes are rare, and so far we haven't. Even more provocatively, he suggests looking for impossible black holes, ones smaller or younger than physics allows, which could hint at mutations in the cosmic gene pool. Yet the deepest implication isn't about black holes, it's about purpose. If universes evolve, does that mean the multiverse has a direction, a drive toward complexity, stability, or even awareness? Some philosophers shudder at the idea, calling it teleology smuggled into physics. Others find it poetic, a universe that births children, inherits traits, and stumbles toward forms we can't yet imagine. Whether it's science or metaphor, one thing's clear: the line between cosmology and biology just blurred beyond recognition. And in this vast Darwinian arena, our universe might not be special. Just lucky. What if the reason our universe seems perfectly tailored for life isn't luck but selection bias on a cosmic scale? The holographic anthropic principle takes the fine-tuning problem and flips it upside down. Instead of asking why the laws of physics allow life to exist, it suggests that only universes capable of producing observers can ever be observed, the rest. They're like empty theaters with no audience, real but forever unseen. And when you pair this idea with Nick Bostrom's simulated reality hypothesis, it paints a picture where life isn't accidental but inevitable. Because reality itself might be a self-correcting feedback loop designed to produce us. Think of it like a cosmic version of the observer effect in quantum mechanics. In the double-slit experiment, particles behave differently when watched. The holographic anthropic principle applies this logic to the entire universe. Suppose consciousness isn't just a passive bystander but an active participant in shaping reality. In that case, the very existence of observers, like us, could collapse the multiverse into a state where life-permitting conditions are guaranteed. It's not that the universe had to be this way. It's that we could only ever find ourselves in a universe that allows us to exist. Every other configuration, no matter how mathematically possible, remains uncharted because there's no one there to map it. Now layer this with Bostrom's ancestor simulations. If advanced civilizations routinely create hyperrealistic simulations of their past, the number of simulated minds would dwarf organic ones. Statistically, we're probably inside one of those simulations, but here's the twist. The holographic anthropic principle suggests these simulations must be fine-tuned for conscious observers, otherwise they'd never run long enough to be noticed. A glitchy simulation where life can't form would crash or get deleted. Only the stable, life-friendly versions persist, creating an evolutionary pressure toward universes that can sustain observers. This might even solve the Fermi paradox, the eerie silence of the cosmos despite its vastness. If civilizations inevitably create simulations, the real universe could be barren by comparison, its resources devoted to running countless virtual worlds. We're not hearing from aliens because they're not out there, they're up there, in layers of reality we can't access, too busy generating universes to explore their own. Critics argue this is circular reasoning. Of course, we find ourselves in a habitable universe. We couldn't exist otherwise, but supporters counter that it's no different from Darwin's realization that life adapts to its environment. We shouldn't be surprised to find ourselves in a universe that fits us like a glove, because every other possibility is, by definition, unobservable. The unsettling beauty of this theory, it doesn't just explain fine-tuning. It suggests reality might be a self-fulfilling prophecy, a hall of mirrors where observation and existence are inextricably linked. Whether we're in a simulation, a hologram, or something stranger, one thing's clear: the universe isn't just allowing life, it might be waiting for it. Quantum entanglement is already strange enough. Particles linked across vast distances, instantly mirroring each other's states no matter how far apart they are. But what if this cosmic connection isn't just a quirk of our universe? What if it's a bridge to another? The entangled multiverse theory proposes exactly that, twisting one of physics' most baffling phenomena into a potential portal between realities. At the heart of this idea lies a jaw-dropping equation, equals EPA. It sounds like cryptic algebra, but it might be the key to unlocking a hidden network of wormholes stitching parallel worlds together. Let's break this down. refers to Einstein-Rosen bridges, better known as wormholes, those hypothetical tunnels through space-time. EPR stands for Einstein-Podolsky-Rosen, the trio who first described quantum entanglement back in 1935. For decades, these concepts seemed unrelated. Wormholes were cosmic shortcuts, entanglement was just quantum weirdness. Then, in 2013, physicists Leonard Susskind and Juan Maldacena dropped a bombshell. What if they're two sides of the same coin, their radical proposal? Every pair of entangled particles is connected by a microscopic wormhole, a thread of warped spacetime so tiny it's imperceptible, but real. This isn't just a poetic metaphor. The math checks out. Normally, wormholes are unstable, snapping shut the moment anything tries to pass through. But quantum entanglement offers a loophole. The equals EPR conjecture suggests these wormholes might stay propped open by the very entanglement that creates them. Picture two pieces of paper folded toward each other, nearly touching. Now imagine a strand of spider silk stretched between them, too delicate to see but strong enough to bind them. That's how entangled particles might communicate, not through magic but through spacetime itself, knotted into invisible tunnels. Now, the million-dollar question: could we ever use this to send messages between universes? Some theorists, like Susskind, argue it's theoretically possible, but with a catch. Any attempt to manipulate the wormhole would break the entanglement, severing the connection like cutting a wire. Others, like Daniel Jafferis, propose a workaround using quantum teleportation protocols, where information isn't sent through the wormhole but reconstructed on the other side, like faxing a document across dimensions. Yet the skeptics fire back. Even if microscopic wormholes exist, scaling them up to traverse macroscopic distances or realities would require energies beyond anything we can muster. And then there's the causality problem. If you could signal another universe, could you create paradoxes like a message arriving before it's sent? The equations get messy fast, hinting that nature might have built-in firewalls to prevent cross-reality spam. But here's the tantalizing part. If entanglement does create wormholes, it could mean the multiverse isn't just a collection of isolated bubbles. It might be a vast, knotted web with threads of space-time connecting every particle to its entangled partners, some of which could reside in other universes. Every time you measure a quantum particle and collapse its state, you might not just be choosing an outcome, you could be tugging on a hidden strand of the cosmic net, sending ripples across realities you'll never see. The implications are dizzying. It redefines entanglement not as a curiosity but as architecture, the scaffolding holding the multiverse together. And it leaves us with a haunting thought. If every particle in your body is entangled with partners stretching back to the Big Bang, how many of those threads lead outside? Are you right now a knot in the fabric of space-time, tied to versions of yourself in worlds where every quantum possibility plays out? The math whispers yes. But until we can peek behind the curtain, the multiverse keeps its secrets woven into the invisible threads between the stars. Forget dark matter, black holes, and even the Big Bang. What if the true architecture of the cosmos is built not on gravity, but on electric currents surging through an infinite sea of plasma? This is the defiant claim of plasma cosmology, a fringe theory that throws out modern astrophysics playbook and replaces it with a vision of the universe as a swirling, electrified tapestry. Picture reality not as a collection of isolated galaxies, but as a cosmic web of glowing filaments stretching across billions of light years, powered by forces we're only beginning to understand. And if its proponents are right, this could mean our universe isn't alone. It's just one cell in an endless, electrified honeycomb of parallel worlds. The roots of this idea trace back to Nobel laureate Hans Alfvén, who revolutionized plasma physics in the mid-20th century. He showed that when electrified gas plasma dominates a system, it doesn't behave like the serene cosmic soup astronomers often imagine. Instead, it twists into ropes of current, sculpting itself into structures that mimic the very galaxies and galaxy clusters we see in deep space surveys. Alfvén's kicker: no dark matter needed, no singular Big Bang, just the interplay of electricity and magnetism on a scale so vast it defies intuition. Enter the Sapphire Project, a controversial experiment that's become the poster child for modern plasma cosmology. In a lab in Ontario, researchers zap hydrogen gas with high-voltage electricity, watching as it self-organizes into glowing orbs and filaments eerily reminiscent of celestial objects. Their most startling claim: under the right conditions, these plasma balls exhibit behaviors that mimic stars, including unexpected energy output and elemental synthesis without the crushing pressures of nuclear fusion mainstream science insists must be present. Skeptics dismiss it as laboratory sleight of hand, but proponents argue it's a scaled-down blueprint for how the universe really works. Mainstream cosmology pushes back hard. They point to the cosmic microwave background's near-perfect uniformity, a smoking gun for the Big Bang, and ask how plasma currents could possibly explain that. They mock plasma cosmology's inability to precisely model galaxy rotation curves without dark matter. Yet plasma advocates counter with anomalies the standard model can't easily explain. Galaxies connected by gargantuan magnetic fields, quasars emitting energy in precise alignments that suggest circuitry, and the infamous empty space of the cosmos being anything but empty, teeming instead with low-density plasma we've only begun to map. Now, stretch this plasma paradigm to its logical extreme. If the universe is fundamentally electromagnetic, and if plasma naturally forms cellular structures at every scale, from lab experiments to galaxy clusters. Could there be regions beyond our observable horizon where plasma has crystallized into entirely separate universes? Some plasma cosmologists speculate, yes. They envision a multiverse not of bubbles or brains, but of cells, each a self-contained plasma universe with its own membrane of double-layer electrical sheaths. These boundaries wouldn't just separate realities, they'd function like cosmic batteries, maintaining voltage differences that keep each universe electrified and alive. The implications rewrite everything. Instead of a big bang, our universe might have ignited when a cosmic zapping session breached the barrier between cells. Black holes, perhaps not gravity wells, but dense plasma foci where inter-universal currents converge, and dark energy, just the push of a neighboring universe's electric field against our own. It's a vision both elegant and anarchic, one where the tools of electrical engineering might one day map the cosmos better than telescopes ever could. Of course, the burden of proof remains. Until plasma cosmology can predict cosmic phenomena as precisely as the standard model, it'll linger on the fringe. But history whispers caution. Many truths began as heresies. Whether plasma universes exist or not, their very possibility forces us to ask, have we been reading the cosmos in the wrong language all along? Not the silent math of gravity, but the crackling poetry of electricity. The answer, like a plasma filament in the void, still glows just beyond our grasp. Have you ever walked into a room and felt an unsettling certainty that you've lived this exact moment before, down to the faint smell of coffee in the air or the way sunlight slants through the blinds? Déjà vu is often brushed off as a brain hiccup, but what if these fleeting moments are something far stranger? The dimensional bleed theory suggests they might be accidental glimpses into higher dimensions, like a 2D stick figure suddenly catching a baffling glimpse of a 3D sphere passing through its flat world. This idea borrows from Flatland, Edwin Abbott's classic thought experiment where beings living in a two-dimensional universe can't perceive depth. To them, a 3D object like a sphere would appear as a circle that mysteriously grows, shrinks, or vanishes as it moves through their plane. Now imagine our universe as a higher dimensional Flatland. When a fourth or fifth dimensional object brushes against our 3D reality, could it leave traces we interpret as déjà vu, glitches, or even ghostly apparitions? Some physicists speculate, yes, these anomalies might be higher dimensional phenomena casting shadows into our perceptual limits, like a hand puppeting silhouettes on a wall. The math behind this isn't science fiction. String theory requires at least 10 dimensions for its equations to work, while M-theory demands 11. Most of these dimensions are compacted, curled up smaller than an atom. But what if they're not always perfectly sealed? Experiments at the Large Hadron Collider have hunted for evidence of extra dimensions by smashing particles together at near light speeds, searching for energy that inexplicably vanishes, potentially leaking into hidden spatial folds. So far, no smoking gun, yet quantum entanglement's spooky action at a distance still puzzles researchers, with some proposing it's facilitated by higher dimensional shortcuts we can't yet see. Then there's the tesseract effect. Just as a 3D cube casts a 2D shadow that shifts shape as it rotates, a 4D hypercube or tesseract would project a 3D shadow that morphs in ways defying our geometry. Could impossible objects like the Penrose stairs or objects that seem to flip inside out be fleeting projections of higher dimensional structures? Neurologists note that déjà vu often activates brain regions linked to spatial memory, hinting that these moments might be misfires where our neural wiring brushes against something beyond its usual coordinates. Skeptics argue that brains are simply prone to pattern recognition errors, but the dimensional bleed theory offers a chilling alternative. What we call glitches are the universe's seams showing. When a fourth-dimensional version of you takes a step left while you step right, the overlap might manifest as a split second of doubled perception. even time itself could be a shadow, a 3D slice of a 4D block universe where past, present, and future coexist. Every déjà vu might be a crack in that block, a place where you momentarily touch the larger structure. The question isn't just whether higher dimensions exist, but whether we're meant to perceive them. Evolution honed our senses for survival, not cosmic truth. A fish doesn't ponder the water it swims in. We might be equally blind to the dimensions lapping at our reality's edges. Yet the clues pile up, from quantum oddities to the brain's uncanny ability to sense something when dimensions theoretically collide. Whether these are true glimpses beyond the curtain or mere neural static, one thing's certain: reality might be thicker than we ever dreamed, and we're just scratching the surface. Imagine a universe where time stands still not by magic, but by the simple act of watching. This is the bizarre promise of the quantum Zeno effect, a phenomenon so counterintuitive it seems ripped from myth. Named after the ancient Greek philosopher Zeno of Elea, who famously argued that motion is an illusion, this quantum quirk suggests reality itself freezes under relentless observation. At its core lies a deceptively simple principle: a particle that's continuously measured can't decay or change states. Like a scared child playing freeze tag, it locks in place to avoid getting caught. But scale this up, and the implications are staggering. Entire universes could exist in perpetual stasis, their timelines halted by some unseen observer's unblinking gaze. The science behind this is as precise as it is strange. In 1977, physicists George Sudarshan and Baidyanath Misra mathematically proved that unstable particles like radioactive atoms decay more slowly the more frequently they're measured. Picture a flickering light bulb. If you stare at it constantly, it appears never to burn out because your observation resets its decay clock each time. Lab tests with trapped ions confirmed this. At the University of Texas, researchers used lasers to repeatedly observe beryllium ions mid-decay. The result: the ion's half-life stretched dramatically, as if time itself had been diluted. It's not that decay stops, it's that the act of measuring interrupts it, like a chef constantly stirring a pot to keep soup from boiling over. Now stretch this effect to cosmic scales. If a conscious observer, or even a machine, could monitor every quantum event in a universe with perfect precision, would time cease to flow? Philosophers have toyed with this idea for centuries. Hindu texts describe the god Vishnu pausing the universe during deep meditation, while Norse myths speak of the frost giant Ymir, whose slumber keeps the world in balance. Even modern sci-fi echoes this. Think of the Matrix's frozen bullets or Doctor Who's time-locked planets. But the quantum Zeno effect isn't fantasy. It's a lab-verified phenomenon waiting for its grandest application. Here's where it gets eerie. If reality requires observation to persist, does that mean unobserved corners of the universe stop existing until someone looks? Some interpretations of quantum mechanics say yes. The moon does vanish when you turn away, not metaphorically, but literally, collapsing into a probability cloud until perception nails it back down. Applied universally, this could mean our entire cosmos is a delicate dance of attention and neglect, with conscious observers as the choreographers. But who or what is observing us? Could our universe be frozen from the outside, pinned under the gaze of some higher dimensional witness, the darkest twist: immortality through surveillance? If a dying person's quantum states their neural activity, cellular decay were monitored incessantly, could death be postponed indefinitely? Russian billionaire Dmitry Itskov's 2045 initiative aims to digitize human consciousness, effectively creating eternal observers of ourselves. Even nature might already exploit this. Tardigrades, those near indestructible microanimals, enter a state called cryptobiosis where their metabolic activity nears zero. Are they unconsciously triggering a biological Zeno effect, pausing their decay until conditions improve? Critics, of course, call this extrapolation reckless. The Zeno effect works on isolated particles, not messy macro-scale systems. And what counts as a measurement remains hotly debated. Does it require intent, or is any interaction enough? Yet the tantalizing possibility lingers. Reality might not just be shaped by observation, but sustained by it. Whether we're lab rats in a cosmic experiment or architects of our own frozen eternities, one thing's clear. The line between myth and quantum physics has never been thinner. And somewhere, Zeno might be smiling, watching us all stand perfectly still. What if the most terrifying parallel universe isn't one filled with alien stars or twisted physics, but one that's utterly empty? Not darkness, not space, not even the faintest hum of quantum energy, just pure, unfiltered nothingness. This is the null universe hypothesis, a theory so radical it suggests absolute void isn't just the absence of reality. It's a parallel reality in its own right, humming with potential in ways we can barely fathom. Let's unpack this cosmic paradox. Quantum mechanics tells us that even in a perfect vacuum, particles flicker in and out of existence, a phenomenon called quantum fluctuations. These aren't just random blips, they're the universe's way of balancing the books, borrowing energy from nothing and repaying it almost instantly. But where does this energy come from? The null universe hypothesis proposes an answer. These fluctuations aren't happening in our universe, they're bridges to a null state, a parallel dimension where the very concept of something doesn't exist. Think of it like bubbles forming in boiling water, except the water is pure nothingness and the bubbles are our reality. Now, here's where it ties back to the birth of everything. The Big Bang might not have been a singular explosion from nowhere. It could have been a quantum fluctuation on an unimaginable scale, a bubble of somethingness erupting from the null. Physicists like Tryon and Vilenkin have speculated that our universe could be one of countless such bubbles, each a statistical inevitability in an eternal sea of nothing. In this view, the Big Bang wasn't a beginning. It was a transition, a moment when nullity hiccuped and spat out a cosmos. But how could nothing be a universe? Imagine a blank sheet of paper. It's not just the absence of writing, it's a potential for infinite stories. The null universe works the same way. Its laws aren't about particles or forces, but about the instability of perfect emptiness. Just as a pencil balanced on its tip must eventually fall, nothingness by the rules of quantum uncertainty must eventually become something, even if only for a split second. And if that something has the right conditions, it might just stick around long enough to grow into stars, planets, and minds capable of pondering its own origins. The most mind-bending implication: if null universes exist, they're the ultimate multiverse generators. Every quantum fluctuation in our reality might be a microscopic Big Bang, spawning pocket universes with their own laws, some collapsing instantly, others ballooning into complexity. We could be living in one successful offspring of an infinite chain of null states giving birth to somethingness, only to reabsorb it moments later. Critics argue this is metaphysics disguised as physics. How can you test a universe that, by definition, contains no detectable signals? Yet supporters counter that the null hypothesis solves a vexing problem: why there's something rather than nothing. The answer: there isn't. Nothingness is just as real as somethingness. It's the flip side of the cosmic coin, the silent partner in existence's dance. And if that's true, then every moment of your life, every atom in your body, is a defiance of the void, a statistical miracle clinging to reality, one quantum fluctuation at a time. From branching timelines to cosmic soap bubbles, from simulated realities to higher dimensional bleed, we've ventured through theories so wild they rewrite the rules of existence itself. The many worlds interpretation suggests every choice you don't make is playing out in another universe, while the holographic principle argues reality might be a two-dimensional projection. The simulation hypothesis dares you to question whether you're flesh and blood or lines of code, and dark flow hints that entire universes could be tugging on ours from beyond the cosmic horizon. Each of these ideas doesn't just add to our understanding, it shatters it, forcing us to ask what is real and how much of reality are we even equipped to perceive. Think about it. If the Boltzmann brain paradox is correct, you might be a momentary flicker of consciousness hallucinating an entire lifetime. If quantum Darwinism holds, black holes could be cosmic wombs, birthing new universes with slightly tweaked physics every time one collapses. And if the null universe hypothesis is true, then everything we know, every star, every thought, every law of nature, is just a temporary bubble in an infinite sea of nothingness. These aren't just thought experiments, they're seismic shifts in how we see our place in the cosmos. So which theory feels closest to the truth? Is our universe one of infinite branches, a simulation running on some advanced civilization's hardware, or a hologram etched on the edge of space-time? Or could the most mind-bending reality be one we haven't even dreamed up yet? Drop your wildest multiverse ideas in the comments. Maybe your theory will be the one that cracks reality wide open. If your brain isn't completely melted yet, hit subscribe and tap the bell. We're just getting started on unraveling the universe's greatest mysteries. From time loops to alien dimensions, the cosmos is stranger than fiction, and the next revelation might be the one that changes everything. Until then, keep looking up and wondering what's looking back.